All right, so let's go over the bonus quiz question real quick. This is what it should have looked like if PowerPoint didn't mess up the formatting on me. But anyway, we have all these plots of pressure versus 1 over volume. We want to know which one is correct for an ideal gas. So when we're answering questions like this, what we want to think about is, of course, the ideal gas equation, which is PV equals nRT. And then what we want is we're looking at a plot of pressure versus the inverse of the volume. So essentially what we want to be able to do is move pressure to one side and 1 over volume to the other side. So we're going to rearrange the ideal gas equation. Pressure is equal to nRT times 1 over the volume. All right, so in a situation where nR and T are constant, you would have pressure is just a linear function of 1 over volume. So it's some constant times the inverse of the volume. And there's no intercept because there's no second term added onto this. So in other words, this is an equation that looks a lot like y equals mx, where m is this constant nRT in this case, and then x is the variable 1 over v, y is pressure. So that's going to look most like A, where it's a straight line and a zero intercept with a positive slope. All right, we can't have a negative slope for the ideal gas law because all these terms are always positive. Pressure, volume, and number of moles, and temperature are always positive quantities. And then this would be a nonlinear function, and this one would be a linear function with a non-zero intercept. So the only one that works is choice A, which is a straight line with no intercept. Okay, so start thinking about how we can, that's one way to sort of think about the equation or some of the types of questions we can ask you about it. But what we're going to do today is finish up some things we talked about last time and sort of see some applications of that. So what we closed with last time was how to calculate molecular speed. So I went through this calculation already, so I'm not going to do it again. So if you want to see the details, refer to the notes from, I guess that would be April 5th. This is where I have the full detailed calculation. Like I said, we're not really going to do these types of calculations on homework assignments or tests, as far as I know. I haven't looked at all the questions that we're going to give you, but I don't think there's going to be anything like this. We're not going to really use this equation, and as I said, it's a little bit of a pain because we have to convert a bunch of units. But what we found was that the root mean square velocity came out to 426 meters per second. So that tells us then that gases are moving really fast. 426 meters per second is on the order of 900 miles per hour, faster than a jet airplane typically goes. So the gas particles are moving really fast. And now we want to see is how do we actually use this equation in more realistic settings or the types of problems that we're going to see in this course anyway. And the two concepts that closely relate to this idea here of molecular speeds are what are called effusion and diffusion. So very similar words that mean very similar things in some sense, but we're going to use this velocity equation, we're going to use that to derive an equation for effusion and diffusion, which we call Graham's law. And that's going to be the type of application we're going to see mostly on our assignments and tests. And you probably will also see it in the chemistry lab if you're taking that as well. All right, so there's two different definitions here, effusion and diffusion. Effusion is escape of a gas through a small hole. And another way to think of effusion is leak rate. So how fast does a gas leak if we have a container with a small opening that the gas can leak out of? And it might sound kind of reasonable or very intuitive to say the rate that a gas is going to leak out of an opening is related to how fast those gas particles are moving. If they're moving faster, then there's going to be gas particles are going to get to the opening a lot more frequently. If they're moving slower, they're going to get to the opening a lot less frequently, and they're going to leak a lot slower. So the effusion rate is, of course, related to the velocity. That makes sense. And then diffusion, which is more directly related to velocity, is the movement of a gas through another gas. So as an example of diffusion, you guys, if you have natural gas in your home, you've probably smelled that natural gas smell. It's not actually natural gas that you're smelling. It's a compound called a thiol that they put into natural gas such that humans can detect it a lot easier. But anyway, those are really foul-smelling, very strong-smelling compounds. If I took one of those and sample that compound and release it here at the front of the room, Diffusion would be a measure of how fast does those molecules and how fast does that smell travel to the back of the room. So the rate of diffusion is how fast those gas molecules move through another sample of gas, travel through space. And that, of course, is also related to the velocity of the individual particles. So the equation for effusion or diffusion, Graham's law, which applies to both of them are, of course, proportional to the root mean square velocity. So as I said, the rate of effusion and the rate of diffusion are going to both depend on how fast the molecules or atoms are moving. So what we do in Graham's law is we write an equation that's a ratio of two rates. So instead of considering individual rates, we write it as a ratio. So the rate of, let's say, gas A over B, the rate of either effusion or diffusion for two gases as a ratio, is going to be equal to the ratio of their root mean square velocity. So that equation that we talked about last time for root mean square velocity was 3RT over the molecular mass, or molar mass, whole thing under the square root. And so we just take the ratio of the two rates, and then we have a lot of terms that divide out here because we're always going to be comparing two gases at the same temperature, and R is just a constant. So we can then rewrite this equation, if we do a little bit of algebra, as the molar mass of B divided by the molar mass of A. So in other words, the ratio of the rates is equal to the inverse of the squares of the ratio of their molar masses. So if we know the molar masses of the two gases, we know the relative rates of effusion and diffusion. And this is the type of equation we're going to be using when we do problems like this. All right, so this is the sort of the standard form of the equation, or the one that's going to be most likely introduced in a typical general chemistry textbook. But there are some variations on this that we can give you, and you want to be aware of these depending on the types of problems you're asked to solve. So we should realize that when we're talking about speeds, which this equation is derived from the equation for molecular speed, remember that from physics, speed is distance divided by time. All right, so this rate equation comes from the equation for speed, which is distance divided by time. So speed is directly proportional to distance. So if we want to rewrite the Graham's law equation in terms of how far a gas travels in a certain period of time, so again, let's say I release two gases at the front of the room with different molar masses, and I measure how far they go in a given period of time, the ratio of the distances they travel is going to be equal to the ratio of their speeds, because speed and distance are directly related. The faster that one gas is moving, the farther it's going to go in a given period of time. The slower another gas is moving, the less distance it's going to go. So distance is proportional to speed. So if we want to rewrite Graham's law in terms of distance, the distance that gas A travels in a given period of time, divided by the distance that the second gas travels in the same period of time, is equal to that same ratio, the inverse of the square roots of the molar masses. All right, so the form of the equation for distance traveled is exactly the same as the standard form, which is in terms of rate. But then let's say we want to measure the time that it takes each gas to go a certain distance. So we might have a problem set up in that fashion. And remember that for speed, which is what the standard equation is derived for, that's going to be inversely proportional to time. So in other words, if we're taking, again, two samples of gas at the front of the room and measuring how long it takes them to get to the back of the room, if one gas is moving faster, it's going to have a shorter time to get to the back of the room. If another gas is moving slower, it's going to take a longer time to get to the back of the room. So when we rewrite the equation in terms of time, we have to invert one side of the equation or the other. So if we're taking the ratio of two times, that's going to be directly related to the squares of the ratios of the molar masses, square root. All right, so in this case, we don't have to invert the ratio on the other side. All right, so there's really two forms of the equation we're going to use depending on whether the information we have or the information we're interested in deals with the time or the rate or the distance traveled. Those are sort of the three possibilities you could have to deal with. All right, so let's look at some examples of this. So first, starting with a very straightforward one, which is just dealing directly with the rates of effusion. So we have an equal molar sample of hydrogen and helium. Hydrogen has a mass of 2.02 grams per mole. H2, helium, which is just He, is 4 grams per mole. That's the atomic mass of hydrogen. And we want to know which one effuses faster and by how much. Remember, effusion is just, the definition is just the leak rate. So if we had a sample of hydrogen and helium and wanted to know which one leaks faster, we can use this equation to tell us. So it doesn't matter which way we set up the ratio. Let's just do it hydrogen over helium, since that's the order they were given to us. We can write the equation in either way. It doesn't matter which one's on top or bottom. So the rate of effusion for hydrogen over the rate of effusion for helium, again, it's going to be the inverse of the square roots of their molar mass ratios. So that's going to be the molar mass of helium over the molar mass of H2. All right, so we have to flip one side of the equation. And so we just have to put the numbers in directly. So the molar mass of helium is 4.00. The molar mass of hydrogen is 2.02 grams per mole. Remember that when we calculated individual rates, the molar mass had to be in kilograms per mole because we were using R, the universal gas constant. But here, because it's a ratio, we can just use grams per mole directly because the units will cancel out, so it doesn't matter what the units are in this case. And so if we just take the square root, that's going to be square root of 1.98, which is equal to 1.41. So this number tells us that the rate of H2 over the rate of helium is 1.41, or in other words, H2 effuses 1.41 times faster. The rate for hydrogen is faster than the rate for helium. All right, so that's sort of a simple, straightforward application. We don't know the individual rates of effusion for each one, but we know the relative rates from this equation are 1.41 for hydrogen versus helium. Okay? Questions? Yeah. If you did helium over hydrogen, you would have gotten the inverse of this, which would be 1 divided by 1.41, which is about 0.7, if I did my math right. And then that would tell you that helium's rate is smaller than hydrogen because the ratio is less than 1. So if the ratio is greater than 1, that means the one that's on top has the faster rate. If the ratio is less than 1, that means the one on top has the slower rate. And you can set up the equation either way. You'll get the same information no matter what. It's just a matter of interpreting it correctly, of course. Okay, so we get 1.41 if we do it this way. We would get the inverse 1 over 1.41 if we did it the other way. But it'd still give us the same outcome. All right, so then let's do one more example which deals with time. So let's say if it takes, we're talking about, again, effusion rate here. So let's say we have, this time, helium and ethane. And let's say we have 1.25 minutes for 0.010 moles of helium to effuse. How long will it take for the same amount of ethane to effuse? So this time we're dealing with the time that it takes something to leak. And again, we can set up the equation either way, with either ethane on top or helium on top. It doesn't matter which way we do it. Since we're solving for the time that it takes for ethane, let's put that one on top. That makes the algebra a little bit easier, but you could certainly do it the other way if you started that way. So we're going to take the ratio of the two times, the time for ethane versus the time for helium. And then again, because this is time, which is inversely related to rate, we have to then flip one side of the equation. So for time, it's going to be the direct ratio of the molar masses, C2H6 over helium. So because we're talking about time in this case, we do have to flip this side of the equation because the heavier gas is going to take the longer time, the lighter gas is going to take the shorter time, and so on. So this is the form of the equation we're going to use. So we just have to do a little bit of algebra. We're solving for the time that it takes for ethane, C2H6. So we just move over, we just multiply both sides by the time for helium. And then we just start plugging in numbers. So the molar mass for C2H6 is given as 30.08. And the molar mass for helium is 4. And then the time that it takes helium to diffuse is given, or effuse is given to us as 1.25 minutes. So we multiply that ratio by 1.25 minutes, and we get 3.43 minutes. So it'll take about 3 times as long for the ethane to effuse as the helium. And when you're doing problems like this, it's obviously, the biggest caveat that the equation is not very difficult. It's not too, there's only 4 terms and the algebra is pretty simple. But keep in mind that you have to make sure that the order is correct. So you should always check that your answer makes sense. So here we're comparing ethane to helium. Ethane is a lot heavier than helium, which means it should move slower, which means it should leak slower and take a longer time. So always check your answer that it makes sense. If your answer seems counterintuitive, it's probably that you inverted one side of the equation and need to revisit what you did. But in this case, C2H6 is much heavier than helium. It should take a longer time for it to leak out, and our answer is in fact bigger than the time that it took for helium to leak out. Okay? And then finally, one last variation that we can do, we have an equation with 4 terms in it. We could set one of the other things as your unknown. So let's say we have 7.23 milliliters of an unknown gas effusing in the same amount of time as 13.8 milliliters of argon in the same conditions. So what is the molar mass of the unknown gas? So here in this situation, we're solving for an unknown molar mass, which the algebra becomes maybe a tinge more difficult, but it's not too bad, right? So we're going to have, again, the effusion equation, the rate for argon over the rate for our unknown, which of course we can set up in either way. And that's equal to the molar mass of the unknown divided by the molar mass of argon, all under the square root. So this is what we're solving for, is the molar mass of X. Keep in mind that because we're giving you the amount of gas that effuses, that's directly related to the rate. So that we're talking about the same amount of time, so the ratio of the rates is going to be equal to the ratio of the amounts of gas that effuses in those given periods of time. Now what's helpful sometimes to do is remember that we can rewrite this equation. If we have a ratio underneath the square root, it's also then the ratio of the square roots. So maybe that's a more convenient form to write it, and then we're going to just be solving for that unknown. Solving for the molecular mass of X. So we have to do a little bit of algebra, which we can either put the numbers in first or do the algebra first. It doesn't really matter. So if we cross multiply by this square root here, we move it over to the other side, we get, and isolate that by itself, the square root of the molar mass of X is equal to the rate of argon divided by the rate of the unknown times the square root of the molar mass of argon. And then remember, we haven't really seen this type of algebra yet, but we should know it from our math classes. If we want to get rid of square roots, we just have to square both sides. So we take both sides and square it. You have to square everything. We do the same thing to both sides of the equal sign. And so then we can rewrite the equation as the molar mass of X is equal to the ratio of the rates squared. So argon over X, quantity squared, times the molar mass of argon. All right, so now we have an expression for the molar mass of X. Again, if you prefer to put numbers in first and then do the algebra, that's fine too. I just did it this way where I did the algebra, isolated the term we're solving for, and now we just have to plug in the numbers. So remember, the ratio of the rates is equal to the ratio of the amounts of gas that effuses in a given period of time. So we see that 13.8 milliliters of argon diffuses in the same period of time as 7.23 milliliters of the unknown. So that's the ratio of the rates, which we have to square and then multiply by the molar mass of argon, which is 39.95 grams per mole. All right, so this is a ratio, so the units cancel, and we just multiply everything out, and we get 146 grams per mole. All right, so again, it's the exact same equation for effusion, diffusion. You really only have one equation to deal with, 2 forms of that equation, and it's just a matter of what variable you're solving for. As we always say, we can do it different ways. Okay, any questions on this one? All right, so now finally, for the first time all semester, I'm going to be talking about something that's directly related to what you do in lab. This was a total accident because, as I said, I have no idea what you do in lab. But I think you guys did an experiment like this where you had 2 gases in a glass tube, and you released them and allowed them to react at some point. So here we go. Here's what's going on here. Okay, so this is a common experiment that people do to measure diffusion. And so, the setup is this. It's a little bit small, so I'll write some things out. We're starting with some gas phase reactant on one side. The classic example is NH3. You're starting with another gas phase reaction on the other side, HCl. Now we know from acid-base chemistry that this is a weak base and this is an acid, so they should react with each other. So when the gas phase NH3 and HCl come in contact with each other, they form, so basically it's an acid-base reaction, so the H plus from the acid goes to the base, and you form an ionic compound, ammonium chloride, NH4Cl. So you're just transferring the hydrogen from HCl to NH3 and ending up with an ionic compound, ammonium chloride, which is a solid. There's no solvent here, so it's going to just be a solid ionic compound. So in other words, the two gases travel in opposite directions. They both diffuse through the tube. I didn't draw that one far enough. And then they meet at some point, not necessarily in the middle, because it depends on how fast they're moving, as we'll see. They meet at some point and they form solid NH4Cl, and that's why you see sort of this white ring here. That's where the two gases, the interface where they've come together and formed the solid product that you're able to see with your own eyes. So that's the, sort of the background of the experiment. I'll sort of write that out just to be clear. So we're starting on opposite ends of the tube with the two gases. And then the two gases, which are in this case ammonia and HCl, they diffuse until they meet. And then once they meet, they react immediately to form ammonium chloride. Alright, so if you're in the lab, this should look familiar. If you're not in the lab, you probably have no idea what I'm talking about, but just follow along. So we're just doing a gas phase reaction inside of this glass tube where we're starting with the two gases on each end, and then they come together and meet in the middle. Alright, now I guess another detail that's kind of important is that the way we set this up is that we plug the glass tubes with, I guess, cotton balls or something that has the aqueous solutions of ammonia and HCl, and then the gas ammonia sort of leaks out of the solution and travels to the tube, and the gas phase HCl leaks out of the solution and travels to the tube. That's kind of how we set it up, and that's the idea. So then what we can do is we can use the diffusion and effusion equation, Graham's law, to calculate how far down the tube are they going to travel before they meet. All right, so that's what this problem deals with. So we're going to react HCl and ammonia. We'll give it the molar masses here. They're released from opposite ends of a tube that is 30 centimeters long, let's suppose. That's 1 foot in sort of English units. How far does the ammonia travel before reacting with the HCl? All right, so again, the diagram is this. We have a tube with a total distance of 30 centimeters across. Ammonia starts at one side, HCl starts at the other side, and they meet somewhere. That's what we're trying to figure out. Where do they meet? And so we're trying to find this distance here, the distance that the ammonia travels before it meets the HCl and they react. All right, and like I said, it's not necessarily going to be the halfway point. So what we should realize from Graham's law of effusion or diffusion is that we have this equation in terms of distance that I introduced. So the distance that HCl travels divided by the distance that ammonia travels is equal to the inverse of the square root of the ratio of their molar masses. So the molar mass of NH3 divided by HCl. Alright, so that's the Graham's law equation in terms of distance, which is exactly the same form as the rate equation, the standard form. So we can put numbers in here. The molar mass of ammonia is 17.03. The molar mass of HCl, so in this case we need to know both, is 36.46. And that's going to be equal to 0.683. So from this we know that the distance that the HCl travels is equal to 0.683 times the distance that the ammonia travels. Okay? Or we could divide both sides by 0.683 and see the relative ratio of ammonia to HCl. Alright, so we're just taking this as the ratio of the two. We just move the NH3 to one side, and that tells us the ratio of the two. But we still have two unknowns, right? Because we don't know the distance that HCl travels. We also don't know the distance that NH3 travels, which is what we're trying to solve for. So we have to write a second equation that deals with the two unknowns. Anytime you have two unknowns, you need two equations. And pretty straightforwardly, we can see that the distance that they travel, if we add them together, has to be equal to the total length of the tube. All right, because they're going to meet somewhere in the middle of this 30-centimeter tube. It's kind of like the classic physics problem. If a train leaves from Chicago going 60 miles an hour and a train leaves from Cleveland going 50 miles an hour, where do they meet? It's the exact same concept. They meet somewhere in between, where the total distance that the two travels added together has to equal 30 centimeters, which is the length that they're, the distance apart that they're starting. So that's our second equation, and we just substitute this into there. So we get 0.683 times the distance that ammonia travels plus the distance that ammonia travels equals 30 centimeters. And now it's a simple linear equation with one unknown, and the distance that ammonia travels is equal to 17.8 centimeters. All right, so you may have already done a calculation like this. If you have the lab, you might have to do it in your pre-lab or post-lab. You've already done that. You probably then measured it yourself in the lab, and most likely got an answer that was way different from this, because this experiment never works as well as advertised, as far as I know. But maybe you were really skilled or really lucky and got that exact number in the lab as well. But theoretically, that's the distance at which they should meet if you're using a 30-centimeter tube. Okay. So any questions on that concept? Okay, so that's kind of you might see homework problems and things like that. That's why I introduced it now. It's just another sort of niche application of Graham's law. I mean, it's not really an important thing we do in chemistry, conducting reactions in glass tubes and measuring where the reaction takes place. That's kind of a pointless demonstration, but it's a good demonstration of the concept, at least. All right, so the last thing we're going to deal with in Chapter 8. Any questions on this? I hear some murmuring, so I don't want to move on if there's still questions. Yes? Do I divide it? Well, so it's this equation, NH3, so then we add these two terms together, 0.683 plus 1 NH3, so we get 1.683 times the distance that NH3 travels equals 30. So this is our first equation, the ratio of the two. This is our second equation, which is the sum of the two. We do a substitution, so we replace DHCl with 0.683 times the distance of NH3. So we do a substitution, then we add the two together to get 1.683 times the distance of NH3 equals 30. Just divide both sides by 1.683 and we get 17.8. So at that stage it's just algebra. But again, two equations, two unknowns, so we have to make a substitution somewhere to remove one of the unknowns so we can solve for one of them. Okay? And like I said, you could set up the ratio either way. You could solve for it, in either direction. You would still end up eventually with the right answer. With the benefit of hindsight, I did this one where the algebra works out the easiest, I think. But the algebra is not that much more difficult if you had inverted these. It's just that you would have had to make some additional manipulations to get to what you finally wanted. All right. So then we could also, now that we know that the distance for ammonia is 17.8, the distance for for HCl is the rest of that distance, which would be 12.2, I guess. Okay, so that they don't travel the same distance; they travel slightly different because of the speeds that they're moving at is slightly different. All right. So the last thing we're going to do in Chapter 8 is talk a little bit about real gases. So everything we've been doing up till now is dealing with ideal gases, which is the ideal gas equation, of course, that we call it. All these behaviors that we talked about, the kinetic molecular theory, the speed that they move at, the Dalton's law, which is the partial pressures, the mixtures of gases, all that stuff deals with what we call ideal gases. And as we're all learning as we progress into our adult lives, that nothing is ideal, and that includes gases. So when we have real gases, we have some differences from the behaviors that I've been telling you about. So remember, for ideal gases, we have this equation that governs everything, PV equals nRT. And that says if you have a gas where the particles aren't interacting at all and there's they have no volume, all those postulates that we had for the kinetic molecular theory, if the gas follows all of those perfectly, then the pressure, volume, number of moles, and temperature follow this equation perfectly. But that's only in the case where all those conditions are met. Now if we take this equation and we put all the variables on one side, PV divided by nRT, so divide both sides by nRT, that ratio should always be 1 for an ideal gas. So if we had an ideal gas and we raised this pressure from 0 to 1,000 atmospheres, let's say, which is a huge pressure, the ratio of PV divided by nRT should always exactly equal 1 if it was an ideal gas, and it would be independent of pressure. So no matter what the pressure is, that ratio should always be 1, but that's not really what we see in real life. Okay, so let's look at how some actual gases behave under these conditions. So if we had hydrogen, H2, a pretty light gas, you would get sort of a positive deviation like this for H2, where as we go to higher and higher pressures, the ratio deviates more and more from that ideal value of 1. Now we can look at other gases that have slightly different behavior. So we don't need to really, internalize or memorize these differences, but we want to know that different gases have different behaviors. They're not all the same. So if we had N2, it would look something like this. You would initially have sort of a negative deviation. It would dip down, and then it would sort of go up from there. So in a very qualitative sense, N2 would look like that. And these deviations are related to the size of the gas particles, like their shape and their mass. So for CH4, we would get an even larger deviation before again turning positive. And if we go to an even heavier gas, CO2, usually the heavier the gas, the larger the deviations are, as we'll see. For the heavier gas, CO2, you get an even larger dip before again at higher and higher pressures, the deviations become positive. So real gases don't follow this ideal behavior perfectly. For an ideal gas, PV divided by nRT should always equal 1. For a real gas, the ratios are going to be different from 1, but it depends on what the exact conditions are. It's not a constant anymore. Okay, so real gases have this deviation, and we're going to start talking about the reasons for those next time. But what we should understand is that the reason that real gases don't behave like ideal gases is primarily for two reasons. And that's related to the size of the particles. So as we mentioned, one of the postulates of the ideal gas law, or the kinetic molecular theory, was that the gas particles have no volume at all, that all of the volume is just empty space. We know in real life that's not true, so the actual volume of the gas molecules or atoms is what causes some of those deviations. And then the other part of it is that the assumption that gas particles don't interact with each other at all, that's also false, and especially is magnified as you go to higher and higher pressures. So if we want an ideal gas to behave, if we want a real gas to behave most like an ideal gas, if we want it to follow PV equals nRT as closely as possible, there are two conditions that we would want to have in order for the ideal gas equation to work best. So the first is a low pressure, because at low pressure, I should start writing in blue, because that's what I usually do. At low pressure, the gas particles are very far apart. So if we want the ideal gas law to work, we need the gas particles to not be interacting with each other. So if the pressure is really low, they're really far apart from each other and they don't even interact at all. So this low pressure situation minimizes interactions between the gas particles. So that's one of the key conditions for ideal gas behavior, is that there's no interactions between the particles. So at low pressures, that's going to be more true. And the other thing about low pressures is because at low pressures the gas particles are very far apart, the volume of the particles themselves is much, much smaller than the volume of the container. Okay? So that's the other key assumption of the ideal gas law, is that the volume of the particles is 0. We know that's not really true, but if you have very few particles spread over a large volume at a very low pressure, that means, to a good approximation, the volume of the particles is very, very, very small compared to the volume of the container, and it approaches 0. So, here we go. That's why I ran back to my office. I forgot to charge this thing, so I anticipated this inevitability. You guys thought you were going to get out of class early, but nope. Okay, so the volume of the particles is much smaller than the volume of the containers, provided that the gas sample is pretty dilute, where there's not a lot of not a lot of pressure packed in there. Now, the other condition that leads to more ideal gas-like behavior is high temperature, because at high temperature the gas particles are moving faster. And they spend little time interacting with each other. All right, so this high temperature minimizes the interactions between gas molecules. All right, so if you're at a high temperature and the gas particles are zooming around really fast, they're never going to see each other. If they do, it'll be for a split second. If they're moving a lot slower, they have a lot better chance of coming in contact and having those interactions that will then lead to deviations from the ideal gas law. All right, so these two conditions, low pressure, high temperature, are going to give you the most ideal gas-like behavior. No gas is perfectly ideal, but under these conditions, it will follow the ideal gas law most closely. And as it turns out, what do we mean by low pressure and high temperature? Typically, the conditions that we operate under in a lab, somewhere close to 1 atmosphere, somewhere close to room temperature, those qualify as both low pressure and high temperature. So if you're working in a laboratory environment, if you do experiments with gases in the lab, which you may or may not do because I don't know what you do in the lab, but if you do, under those conditions, the ideal gas law, PV equals nRT, works pretty well. So you don't have to worry about those deviations in most cases. If you're working with gases, common gases like O2, nitrogen, and you're working at room temperature and pretty low pressures, then the ideal gas law works very well, and those are the conditions where the ideal gas law is going to work the best. But for real gases where we have deviations, if we go to, again, very high pressure or very low temperature, or we have really heavy gas molecules, those are the ones that are going to deviate the most from the ideal gas behavior. And that leads to what's called the van der Waals equation, which is a modified ideal gas equation. So it's a modified equation that deals with the fact that real gases have these deviations. We're not going to use this equation to do calculations, but we do want to understand what it means. Question? Well, it also depends on the volume. So, yes, but if you have an infinite volume, then the pressure also trends to zero as well. So it requires you have a very large volume too, so that when you raise the pressure, when you raise the temperature, the pressure is still low. So those are kind of the two limits that you want. You want, I didn't specifically mention volume, but you want large volumes, low pressures, high temperatures. In those extremes, that's when you're going to have the best ideal gas behavior. Okay, good question though. All right, so for real gases, we have the van der Waals equation, which I'm going to give you and explain to you, and you should understand what it means, but you're not going to really do calculations with it. So what we do is we modify the pressure by this term here, n squared A over V squared. So N and V still have the same meanings, moles and volume. We modify the volume by this term N times B, and then we're going to set that equal to nRT. All right, so in other words, we're going to put a fudge factor on both the pressure and the volume that accounts for the deviations that real gases experience. So what do these terms mean? All the other terms are the same: pressure, volume, number of moles, and temperature, same as the ideal gas equation. But these terms A and B are what we call the van der Waals parameters. So A is going to adjust for the interactions between particles. So as we'll learn in Chapter 9, the interactions between molecules tend to be attractive in nature. So if you have these interactions between the molecules that are, they're going to start sticking to each other, they're not going to hit the walls with as much force because they're going to be attracted to each other and not hitting the walls as fast. So basically this is an upward modification of the pressure. The van der Waals term A should be a positive number in almost every case. You're going to adjust the pressure upwards to account for the fact that the measured pressure is a little bit smaller than what it ideally should be because the gas molecules are attracted to each other. And then the B term is going to adjust for the particle volume. So in other words, B is the amount of volume that the gas molecules themselves occupy, and so we're going to adjust the volume by that. We're going to subtract that from the volume, such that in the equation we only have the volume that's completely empty space, which is what the ideal gas law assumes is going to be true. So those are the two adjustments we make, one that accounts for the interactions between particles, one that accounts for the non-zero particle volume, and in sum what we call those A and B terms are the van der Waals parameters. So these are experimentally determined parameters, so they're not something that we can calculate or know from first principle. They're completely empirical, so they're tabulated for a bunch of different gases, and they depend on the type of gas they're talking about, so they're unique for each different gas. Alright, so the van der Waals parameters A and B are going to be different depending on what gas you're talking about. They're not the same for everything. Alright, so these essentially are just experimental fudge factors that we add to the ideal gas equation to make it work better for real gases. So all of our questions on real gas behavior is going to be conceptual in nature, so if you do the homework assignments this week, you'll get a good feel for how that works. Maybe next week you'll even see some more. And then we're going to start the very last chapter on Monday, which deals with condensed phases, liquids, and solids.